So, thank you, Alexander. Good morning, ladies and gentlemen. We learned in the first presentation from Anders something about central heating and cooling systems, and so we missed most of the equations Reinhard intended to explain to us. So I will promise you I have one equation and I try to explain it. All the other things are just some words. So what we learned in the first presentation was that economy of scale and integration of high density heat or cooling demand will be a good idea to come up with a central heating or central cooling system. So what I'm going to explain you is why it makes sense besides economy of scale. So the first question I'd like to go through is how do we come up with a heating demand, and then I'm trying to explain what are the benefits from that. So most of you are pretty much aware that we will have different applications which will produce a heat or cooling demand, but most of these applications have a main trigger. So the most important thing for heating demand on a certain temperature is space heating. If you would like to have a certain temperature in a room, you need to heat it, probably you have to cool it, and the space heating demand depends mostly on the outdoor temperature. You can see this if you follow the weather conditions in the last few days. So this morning it's quite cold outside and we have to heat up the room. Another point is domestic hot water, and then we come up with some more technical issues, which is dehumidification in kind of, if you have air conditioning and you need to have a moisture control, which is not very important in Central Europe, which is more important in, for instance, different climate conditions in the US or in other areas of the world. And one also important thing is technical or industrial process heat. So for instance, if you have sterilization in hospitals or something like that, or you have an industrial process and you have some plastics and you need to put it in a certain shape, you can heat it up, and you probably use a kind of heat to do this. And what determines the magnitude of the heat load or the heat demand, mostly since space heating is the most important thing in most cases, we have the climate conditions and the weather conditions, while climate is a long-term weather condition. Weather condition is the recent state of the atmosphere at a certain point of time. And then we have the building utilization and occupation. So if you have a housing area and which is not occupied, so you won't have, for instance, you have some space heating for moisture control or whatever, but you won't have domestic hot water demand. And then certainly the technical and industrial processes will determine the magnitude of the heat load. So if you have a look at different kind of buildings and kind of the types of using the buildings, we will have housing areas as a building type for single and multi-family housing. If we think on army installations, these are mostly barracks for troops or whatever. And then we have offices, we have some kind of jobs with public access, so always open doors, people coming in and going outside. We have education and training areas like this. We have hospitals, clinics, we have industrial processes. And other most important impacts are size of the buildings, the building physics. Meaning what are the external losses through insulation and the wall to outside and the windows and such. And then we have internal heating sources. So here are some computers inside. We have electric lighting, and we have other electric applications, and everybody of you radiates some kind of heat into the room. So we have external losses, external internal heat sources, and we have a number of air changes. So mostly you have to replace the air in a room like this, like 3 or 4 times a day. So if we have a look at that in total, you can see here annual load curve for heating and an annual load curve for electricity. And you can see, if you look at it, a main difference. In space heating and domestic hot water, we have a seasonal shape. And in electricity, we have almost no seasonal shape. This is for a city in Germany with like 300,000 inhabitants. And there you can see that the electricity demand in summer is a little bit lower than in winter. If we go to US cities, it's probably vice versa, since we have electric air conditioning. So the electricity demand is probably a little bit higher in summer. But you can see in the electricity load curve that we will have a weekly shape. And in space heating, we have just a seasonal shape. And the main reason for that is that space heating is the most important part of this load curve. And if you have a look at this slide, you can see a diagram with a heat demand. Each cross is the demand for 1 hour, shown over the outdoor temperature from minus 15 centigrade to 45 centigrade. And what you can see is that the lower the outdoor temperature is, the higher is the heat load. It's quite easy to see. And then you can see, do I have a laser pointer? Yes. This is the domestic hot water base. So this is mostly independent from the outdoor temperature. It depends more on number of showers and all that. So, and now I need to explain one equation and one important thing. Most people think that heat and temperature is pretty much the same. It's not the same. Two completely different things describing an amount of a kind of energy, a physical situation. So consider you have two vessels with hot water. Both are filled with 1 liter, for instance. In one vessel, the hot water has a temperature of 50 centigrade. In the other vessel, we have 1 liter of water with 100 centigrade. So in terms of energy, calculated to 0 centigrade, the amount of heat energy in vessel A with 50 centigrade is about 100 kilojoule. This is quite the same like a battery in your car to start it, a 12 volt block. And in the other vessel, we have the same amount of water. The temperature is just twice as high, so we have 200 kilojoule of heat energy. If you put them together, you have 2 liters with a heat energy content of about 300 kilojoule. But the temperature is not 150 centigrade, it's 75 centigrade. So you can summarize the heat energy but not the temperature. This shows you that temperature and heat energy are two different things, which is quite important. And now we're coming to the point of why I'm explaining this. If we consider a central heating system or a heating system, we need to know one equation. The heat energy we need to meet the demand is, in case of hot water systems, the mass of water or the amount of water, a physical description of the heat capacity, so the amount of heat water can store, and the temperature difference between two different temperature levels. For instance, the temperature you supply to the building and the temperature you have in the room, or the return temperature when you bring the water back. So in case of space heating, the delta T is the difference between the temperature of the heating source, for instance, and the room temperature. And this explains you which amount of heat you need. And this is the link between heat and temperature. So why I'm explaining this? Because we have different kind of applications. I tried to explain a little bit earlier. And these different kind of applications require different temperatures. So here's a mistake inside. The first application should be domestic hot water. We need temperatures higher than 60 centigrade to have Legionella prophylaxis. We have space heating. You need temperatures between 35 and 90 centigrade, depending on the heating system in the building and the size of the heating source inside the room. So if you see these radiant heaters. If they are a little bit larger, you can increase the amount of water and you can reduce the supply temperature in this room to this radiant heater. If you have smaller ones and you have the same heat load in the room, you need to increase the temperature because the area for this, or the area of the radiant heater is a little bit smaller. For dehumidification, we need temperatures about 70 to 80 centigrade. If you go to a hospital and you need sterilization, we are talking about 120, 150 or 180 centigrade. And in technical processes, they start with some chemical processes, 35 centigrade, and they end up in temperatures which are much higher than 200 or, for instance, 300 centigrade. Depends on the process, and an important use of heat, mostly in army installations, is steam cooking, where we come up with temperatures like 140 centigrade, 150 centigrade. So the interesting thing now is if you have a look at the daily heat load profiles of different kind of building utilizations. If you see the housing, you see two peaks. This is a morning peak typically and the evening peak. This is the magnitude or the height of the peak depends on the season in which we are in and the outdoor temperature for sure. But mostly you have in the morning, let's say if the people are leaving the house at 8 o'clock or 7:30 in the morning, you start heating like 6 o'clock or 5:30 to heat up the rooms a little bit. Then you have in the afternoon when you come back, you would like to have a warm room before, and then you start heating again like 4 o'clock p.m. And this is the second peak. Mostly this peak is a little bit tighter but higher. Then we have the domestic hot water base. There you can see this is running, depending on the domestic hot water preparation system, like a constant load through the day, because you have mostly a storage heat loading system. This means if you have a shower, you will have a kind of storage like 150 liters, and you use this water, and when you are showering or if you do the dish washing or whatever, and then you will reheat it again, and this is a kind of a quite constant load through the day. If you go to an office building, which is occupied from 8 o'clock to, let's say, 4 o'clock in the afternoon, there you can see that these office buildings are mostly occupied through the day. You start a little bit later to heat the rooms, and in the afternoon you stop heating, but you can see there are, in most cases, not such peaks like in these housing areas because the rooms are occupied through the day. The same in hospitals or in clinics, but there you mostly have a domestic hot water demand. And this is the reason why it's a little bit shifted from the x-axis. And if you go to a training or education area, this depends on the occupation of this area, but mostly you have, for instance, in a school or whatever, in the morning an occupation and less occupation maybe in the afternoon, and mostly no domestic hot water demand. So if we transfer this now again to our comparison of those electricity and space heating demand, you've got an explanation why you have this, we call it bath tube shape of space heating and domestic hot water demand. All the buildings you integrate and connect to a central heating system, the same as in a central cooling system, they end up with this load curve. So the interesting thing is now, if you overlay them, you can see on the left-hand side the red curves. We have the different peaks and the different shapes and the shifts from zero all through the day. And if we summarize it, we will end up in a curve which has a little bit different shape. You can still see the peaks, but the peaks are not that high. And what happens if you summarize them? You will have a factor of coincidence. So peaks and low marks will balance out each other to a certain extent. Not all buildings have their peak load and their minimum load at the same time, and the load the total load, when you summarize it, is less than the sum of the single peak loads. And this is a very important thing. If you have 3 buildings with, for instance, 100 kilowatt, and you put them together, the peak load is, if the peak is not at the same time, not 300 kilowatts, it's, for instance, 250 kilowatts as a peak load. And so the minimum load is a little bit higher, and the peak load is a little bit lower. So the daily and annual duration curve has less, now I'm missing the expression, interval. Different order of magnitude between peaks and low points. So where does it come from? If you have a look at one building, it's just the same. You have a number of rooms, and you have different temperature requirements in the rooms, so a little bit higher in bathroom, a little bit slower in sleeping rooms, in offices somewhere in between, living room a little bit higher and a little bit lower in the kitchen, because you are cooking in the kitchen, you have the refrigerator, the dishwasher and such, and there you have some higher, some more internal winnings, and so the temperature can be a little bit smaller. And now have a look at the time when you are using the room. You are not at the same time in a bathroom, in an office, in a sleeping room, and in your living room. That means if it's cold outside and you would like to have the highest temperature, because you would like to have it very ambient and comfortable in your living room, you're probably not heating your sleeping room because you have it a little bit cooler. So not all the heat units in your rooms have the peak at the same time, due to the fact that you are not, if you have a 4-people family, you are not using all the rooms mostly at the same time. And this is something that happens if you interconnect different buildings with different utilizations, occupations, and different kind of use and purposes in a central heating system. And this is something we call the factor of coincidence or coincidence factor. And this is a very important thing, because this offers us a lot of benefits. So if we lay out the piping system and the generation equipment, we are going to design it for the total peak load or the assumed future total peak load. And this peak load is less than the sum of the single peak loads due to the load profile through the day and through the year. This reduces, beside the economy of scale, Anders explained a little bit earlier, this reduces the capacities we need to install, and this comes up with a reduction of first cost when we're going to install it. So we have 2 economic impacts. The first thing is in a district heating or cooling system, we have this economy of scale compared to a single building heating system, and we can benefit from the coincidence factor. And also the operation of the equipment is more efficient if we have different load profiles and we bring them together, and the delta between peak and minimum point is smaller. The generation equipment can be operated a longer time through the year in their operation best point, and it's more efficient. So this will also reduce the amount of primary energy and increase the energy efficiency. So Alexander explained before, as starting point, before Anders started to talk, that central heating systems and cooling systems can mostly be found in dense areas. So if you integrate those buildings, you would like to add those buildings to this quite costly central heating and cooling systems due to the large piping system, where you have a very high heat density. What you're going to do is you should analyze the existing building stock, calculate the heat loads, as I explained a little bit earlier, and you should calculate the annual energy demand, so the peaks, the lowest points of each building, the duration curve, and then you should analyze the building utilization, occupation, and if possible the building physics. If you have an army installation, it should be quite easy. It's a little bit more difficult if you have a look at a large city like Copenhagen, where you miss a lot of information on those buildings. And then you should evaluate the option connecting those buildings to a central heating or central cooling system. In the figure on the right-hand side, you can see different kind of building usages given by colors. So the red colors are housing areas, and the yellow colors are different. You can't see those yellow colors quite well on this slide, but there are some different kind of municipal areas with industrial or other uses. And then you can calculate the heat load of each building, and you can summarize it. You can see here each red dot is a building with a certain heat load. In Smethport, somewhere in the Midwest in the USA, we made a heat load analysis for this very small town, which intended to add all the buildings to a central heating system fired by a wood chip boiler. And then we put them together in a square pattern, and we calculated, this is given by the colors in the squares, we calculated the total heat load or the total annual heat demand in each square as sum of the buildings. And the darker the color is, the higher is the density. It's not very surprising that the density in the central areas is the highest, and if you go a little bit outside, you can see the density is much lower. But you can see, this is quite interesting. There we have a square with a heat load which is a little bit higher than in the surrounding squares. This depends on one big user or one big building. So the idea behind central heating and cooling systems is find one big building and justify in terms of economics the piping connection to that building, and then make it a little bit larger and try to connect the buildings on the way to that. It's like building a bridge across a river. If you have one building which justifies you more or less to the pipe connection to that building, you should also connect the buildings on the way to that building. So you can see here another example of a heat density map in a mid-sized German city in the south of Germany. And yet there you can see this blue line, the scattered blue line. This is the idea where we have some huge buildings which should be connected to the existing system in the southeast. And there we used this heat density map to figure out which is the most interesting and most in terms of economics and amount of energy, the most efficient stretch to connect those buildings in the southeast to the existing system. So, and this also helps you to figure out which is probably the best way to go with a pipe. So you can also do this with a level of detail 3 GIS model, which means you have a laser scanning of all the buildings, and you can calculate automatically, including some kind of utilizations and occupations and building physics for each single building. The heat load again, you can come up with a heat map which shows you in this very highlighted areas, there probably makes sense to figure out if a central heating system will make sense, and it probably will make not much sense if you go to this low density areas. And one other important thing, we've seen something on Rhino slides, and we probably hear something about in the next few talks. The upper figure shows you a load curve through the year, and you can see also again this bath tube shape. And then we started to put it in a certain order in the figure on the bottom of the slide. We just sorted by the highest heat load to the left-hand side and the lowest heat load to the right-hand side. So what we are losing, if we do this, we are losing the shape through the year but we keep it in mind that we have a shape of the year. But in this lower figure, we call it load duration curve. You can see what is the highest load and what is the domestic hot water base. And then the different colors shows which piece of generation equipment produces or generates the heat you need for that. And then you can easily calculate the number of running hours and the amount of energy you need from this equipment and the amount of primary energy you have to put in. So, and then you can easily transfer this in dollars or in euros and calculate the economics from that. So the space under both curves is absolutely the same, and it just put it in a little bit different kind of shape. You can easily recalculate it. So what is the conclusion from all that? First thing is that the building physics, size, utilization, and occupation determine the heat load and the load profile. The heat application and the outdoor temperature determine also the load profile and the order of magnitude. The building heating system, the amount of domestic hot water and process application determine the required supply temperature you need to supply to the buildings. And this is the lower limit for your supply temperature. Different buildings with different load profiles can be integrated into one system, and finally you come up with a factor of coincidence. This means that the annual heat demand is the same, so in terms of BTUs or in terms of megawatt hours per year, but the peak load and the minimum load in terms of BTU per hour and the megawatts is less than the sum of each single building. And in consequence, this factor of coincidence offers you the opportunity to reduce first cost and increase efficiency of the equipment all through the lifetime. Thank you.
Very good. Well, thank you very much, Stefan. Now we go to the next step, and we would like to look at what are the losses and the costs of your distribution systems, because that's probably the major concern for people who want to use systems, how much it will cost to build this network, and how much energy will be lost in the systems, and different perceptions about that and misconceptions. So I just wanted to ask expert in all this economics from Danfoss company, Oddger, to talk about this effects. Our next speaker is Oddger Gomenson from Danfoss company, and he will be talking about efficiency and economics of heating and cooling networks compared to decentralized options.